Hello everyone, welcome to the second lab of prime time of unit 5. In this lab we will focus on the post layout timing analysis. So we will talk about, we will practically see all the concepts that we have been discussing in the lecture sessions of unit 5. We will look at the propagated clocks, we will look at the parasitics, we will look at the OCV settings, timing the rates, TR, and so on, right? So we will focus on this, and also during this whole session, please make a note of. I'll keep pointing on the important things that differ between pre-layout and post-layout, and just please make a note of it. Obviously, it is also mentioned in the lecture sessions also. So it will just try to make a connection between what changes when we go from pre-layout to post-layout. So our design is this design comes from one of the synopsis examples. So this is the design Orca routed.v. This is an Orca is a small CPU. I think it's open source CPU, a small CPU. It has a clock generator. So it has various blocks. It has a clock. It has multiple. The good thing is that it has multiple clocks. So we'll also look at the cases how to deal with multiple clocks. This is the top level Orca, and inside it has some memories also. Some clock generation logic, there's a PLL also, so it's a good test case for us to do. We also see, let's take a look at the parasitics also. How does the parasitic file look like? So this is .spef. Spef is the header explains what are the units. So the important thing is here is the capacitance unit and the R unit. There also L unit is specified, but there are no L extracted. So since inductance is negligible, the extraction tools will not extract the inductance at all. So although L unit is present here, but there is no inductance available. So it has the first section here. Then it's the name map section, where a number is assigned to every port and every net, every pin, every port. So that means all nets. So parasitics are characteristics of nets, not cells, right? So and a net is a connection between two cells. So for each of these nets, for each of these pins of cells, let's say a buffer connecting to a buffer, the net, this spef will mention something like this, that the RNC of a particular net between point A and point B is something. Now the point A will be, for example, point A will be output pin of a particular cell, point B will be input pin of a particular cell. All such pins are given some numbers. So this is the first section here. The name map is given, is assigning some numbers to various pins. For example, see this, the I Orca top, I PCI core, U cell. This is a number, is assigned a number. Similarly, these are input. So power save is an input to this chip. So this is a complete chip. It even has pads. So it's kind of a small chip. The design is kind of a small chip, and so every there are various numbers here. Now if we go forward, there will be a lot of numbers. And now let's go in the. So now for every so there is a cap section. So this is a net. So the section is a D net, and it's assigned. It's connected from a number, and so this is the connectivity from something I, so to something Zn. So this is the way it shows the connection. And for this particular net, it will show what is the. So these are the segments. These are the net segments 1, 2, and 3 for this particular net 43085, and it is given the capacitance of the net with respect to the ground. So it might also have the coupling cap, but I don't see it here. I need to double check it in prime time. But this is the way spec looks like. It has resistance, and for each net it will have, let's say for each net it will have a cap value, a cap table, and a resistance table. And these are the nodes: colon 1, colon 2, colon 3. So You can even try to pick up a particular net and see. So as an assignment, what you can do, you can pick up a particular net in a netlist and correspondingly try to search for that net's RNC value in this form. So this is a good assignment. That way you can understand better how the syntax works. I can do this here, but it's not that important, and it will take some time because Spef is a big file again, and searching through it takes time. So you can also do this kind of debugging in time also. So now, so we will use this design for this particular assignment. Let's go to the work directory and open SwayamPrabha. Now I have already prepared a script. So we will again study what all goes into this script. Many of the sections are familiar to you. Some of the commands that are new will be specific to post layout. So we will first set the search path. The link library here is slightly big because it contains so many memories: RAM 32, 32, 16,028, and so on. So clock, it has a clock multiplier and a PLL. So clock multiplier and PLL both are coming from this library special.db. Memories come from RAM something.db. The IOs are also present here, so the IOs come from iomax.db. So it is a very common phenomenon because for each of these the vendors might be separate. The standard cell vendor is usually separate than memory cell. Even if the same vendor is providing the library, they will prefer to separate out these. They will give standard cell as one deliverable. They will give memory as another, IO as another, PLLs as another. So your full chip STA link library list will be pretty long. So we will set this. So we set the search path and the link path. Then we read this file and link it. So it shows that it is loading so and so libraries. This information, removing 24 unneeded designs, what it tells us is that prime time to save on memory space, it will load up the full chip, whatever the complete netlist, and it will only keep limited information about the internal design. So you cannot change the current design. However, link has an option. So if you do a link minus help, link has an option, keep sub designs. So it will keep all that 100% design info after linking, so that you can change to that particular design. But this is not recommended since usually STA is carried out at the top level of a particular block or a particular script. So it is recommended to do just link and let prime time remove some information related to the designs that are within the hierarchy, and it is not leading to any loss of information. For all timing purposes, it is not leading to any loss of information. It saves on some memory plus, but the only thing is that it won't let you, prime time will now won't let you change the current design to something else after you have linked the top design, right? So this is the only disadvantage. So this is the default behavior of link. It will remove the unneeded designs. So it does give some message regarding to the operating condition, but we will set the operating condition separately. Now the important command here is specific to post layout is read parasitic. So this is the command. So we will tell what is the format, and we will read this spec which is for this design. And now it will give some message about some information, and if there are some errors, it will produce them here. It is very important to understand those errors. Those are slightly so those errors would be related to whether it is not able to find any net which is given in the spec but not in the netlist, or there might be cases where the nets in the netlist don't have any corresponding nets in the spec. So it will give errors regarding that those nets. So if an extra net is present, so if any such mismatch occurs, it means that the netlist that you have and the spec that is extracted has some mismatches, and most probably the netlist you have or one of these steps needs to be updated. So the backend lead who is giving you this step, or if you are the backend engineer, if you have a mismatch, then you need to make sure that this you are taking the same net list which you used to do the extraction. It is very necessary to do that. If you see errors like missing net in one of the net list or this stuff. Now, if there is some extra net in this step, fine, it will give an error. But if there is some nets which are not present in this step, then prime time will use biload models to. So by default, when after you read parasitics, if prime time is not able to find any RNC for a particular net in this step, it will complete it using biload model, and it is not recommended because you are working at a post layout stage and you should resolve all the errors before signing, right? So it tells us there are 0 errors. How many annotated nets? That means these many number of nets have resistance present in the step and they are annotated. So these are the total annotated nets. These are the capacitances and resistances. So each net can have multiple caps, multiple nodes, and different resistances. So it says that there are the coupling capacitance is 0. We will look at if I am able to find. And let's do one thing. We will do remove annotated parasitics. So remove annotated parasitics will remove whatever annotation. So this process is called annotation. So we could do remove annotated parasitics minus all. We will read the parasitics again. But let's look at the help first for this read parasitics. It's a very expensive command. So the important things here are that this complete with completion time. This tells prime time that if you do not find any nets in this step, complete with either 0 or biload model. That means apply a biload model or don't apply anything. Lumped cap, if you are reading step, you should not use this option. Pin cap included. This tells PT that the RC network includes the pin capacitances. In most of the cases, the RC network inside step will not include pin capacitances. Pin cap will come from the library itself. Increment is something where you are reading multiple step files, hierarchical step files. Then you have to use increment. Path prefix, increment are used to when you are reading. So, for example, a chip level has multiple blocks, and each, let's say if it has 5 blocks and all 5 blocks have been laid out separately, so there will be separate steps. So you will use minus increment and minus path option to annotate the step at a particular instance path. And this is important. Keep capacitive coupling. Let's try out keep capacitive coupling. Is like for if the step has capacitive coupling and you want to do signal integrity noise analysis, then you have to turn this option on. Let's see if it gives something. Okay, it tells us that annotated coupling capacitance is 0. That means although we gave keep capacitive coupling, but it tells us that annotated coupling capacitance is 0. That means it does not have any coupling data, and we will not be able to do noise analysis on this circuit. So a very useful command is report after you read in this parasitics. A very useful command is report annotated parasitics. The help it will so it tells us, it gives a summary report of what is annotated and what is not. So you can do a lot of you can do it on a particular net. You can do it for internal nets, boundary nets, driverless nets, loadless nets. There are so many options. Let's just do the default thing. So it will give certain messages. So even if there was no error reading the parasitic, this is the first case. So fine, all the so there is no mismatch in terms of the nets and pin names between the step and the netlist. That is true. But now it is saying that there are some RC annotations that are incomplete, right? And in the summary, we can see that so there are 2 types of nets: internal nets and boundary nets. Internal nets are pin to pin. Boundary nets are those are coming from ports. So this pin to pin not annotated 0. The first one is very important. RC network for all internal nets is completed, not annotated 0. So there is no problem here. Good. Now it comes to driverless nets. Now usually driverless nets, the nets are without drivers, so they are kind of hanging nets. Usually any problem here not annotated 24 is usually okay to have. It's not a serious issue because that net is not driving anything. Loadless net, again it is correct here, not annotated is 0. Boundary, there might be some problems like this. So 71 are not annotated for boundary port net, and you might need to debug it. You might need to debug with the backend engineer, or if you yourself have a backend engineer, you might need to debug why the port nets are not annotating. So many times the port nets are usually lumped into some value, the capacitance is lumped into some value. Many times if there are pads involved, then such cases can occur. So it depends on case to case basis. But as an ST engineer, this is the most important thing. Internal network should be completely annotated. Now, although it is giving some messages here that ignoring the incomplete, so for example, if you look at this, driver pin is missing in the RC annotation for this particular net. So it might happen that there is nothing which is driving this. Let's look at, so for a particular message, you can look at what it means by doing a man on this. So it tells me, it tells us that you receive this message, informs you that RC network on a specified net is ignored because it is incomplete. The specified pin is not physically connected to RC annotation. So you probably have to debug this and make sure that it's okay to know. So there are many errors and warnings that you can wait, but only after careful checking, right? So we have now read the parasitics. So now we are not working at a bar load model level, we are working at an RC level. Now we will set the operating condition, and now this is very important, on chip variation. We will set it to on chip variation. Analysis type is on chip variation, and we have, this is the operating condition. So this is the 130 nanometer library, which probably explains why there is no coupling capacitance. It might be negligible. So this is the worst case operating condition. And now we will be working at a worst case in the worst case format, because we have read the all the max dBs. So correspondingly there will be min dBs for min format. Now we will create clocks. We will create some clocks. So there are now 3 clocks here: sys clock, P clock, and SDR clock. We will create each of these clocks. So now we are up to constraints. So we will create this clock. I have assigned some periods. I am not sure what the specification of this chip is. I have just assigned some periods myself. Sys clock, P clock, and SDR clock. Now there are 3 clocks. Now there is also a generated clock that we need to define. The generated clock is at the output of a. So let's go at the syntax. This is a generated clock. I have given a name. I have seen multiply by 2. Because this is what we spec, what I understood from the netlist. This is the source. So this particular block ICLK mul is a clock multiplier, and I have seen from the netlist that at this input it gets sys clock, and output is this multiplier's clock 2x thing. So I'll show you in the netlist. So what I'll do is I'll create a multiply by clock, multiply by 2 clock at this output. And the source I am giving as this. I can even give source as this, because this is the clock that reaches there. So you can give source can be any pin before the generated clock creation point. So source can be before any pin before this in the panel network. So I am creating this clock now. So now I have created all the clocks. Now the next is that you should specify what is the clock relationship between the clocks, among all the clocks. Now in this case, what I have learned from the netlist, or what I have seen from the earlier timing reports I saw, is that these 3 clocks are not synchronous to each other. Anyway, let's assume for once, let's not assume anything. So we will not give any false clocks, right? Now let's say you are driving, you are writing the constraints, and you know that these are the frequencies 15, 5, and 12. And now you don't assume that they are either false, they are either asynchronous or synchronous. However, one thing is clear, that the periods for 5 and 15, yes, the periods are some simple multiple, but for 5 and 12, it's not a simple multiple. Even for 12 and 15, it's not a simple multiple. So one thing you can deduce from the frequencies itself, whether they are synchronous or asynchronous. Secondly, you can see whether what source they might be coming from. So typically, if at a chip level you are working at a chip level, and at a chip level, if two clocks are coming from the outside world, most probably they will be asynchronous. Why? Because since the routing resources, people want to limit it, engineers want to limit the routing resources, especially for high frequency signals like clock. There is no reason, in most of the cases, there is no reason to provide two synchronous clock at the chip level or even at a block in a layout block level, if it's not absolute necessity. If the two clocks are coming from two separate PLLs, does not depend what period they have, they should be declared as asynchronous. Now let's say we want to, the other case is of the generated clock. Now this generated clock is generated from sys clock. Sys clock 2x is generated from sys clock because this is this pin gets sys clock. So now let's do a simple update timing code. Okay, let's not apply any false paths and let's proceed now. So let's not apply the false paths for now. We will apply clock uncertainty, and now clock uncertainty here will be a much lower value. Earlier we used to set 0.3, 0.5. Now I've set it to be 0.1, but it should be a lower value than pre-layout because now the clock network is in place. It will calculate all the delays. The skews will be real. The only thing which will be part of clock uncertainty will be most probably clock data and nothing else, or some margin if you want to have. So I apply clock uncertainty. Very important, giving the propagated clocks. Set of clock, or we will set all clocks to propagated mode. Only then prime time will calculate all the actual latency, all the actual network delay. And then I'll group paths. I find it very useful to group the input-output path group into separate to make sure I have different groups for input group and a different path group for the output group. Then I will enable this. I will enable the CRPR pessimism removal by setting this. Set timing remove clock recurrence pessimism to true. I'll enable this. If not, it will not give me CRPR credit. We'll see how that happens. Then I'll set the timing delays. Now this is a worst case scenario, although I should ideally set the timing delay, the late timing delay to 1, but I'll set it to just 1.1 just to show you what effect does it have. So I will set the timing delays, and then that's it. So what is special for post layout? Timing delay, turning CRPR on, propagating the clock, reading the parasitics, setting it to OCD. So these are the important things. You read the actual parasitics. By doing set propagated clock, you are forcing prime time to calculate all the proper latencies. By applying timing delays and setting the chip to OCD, setting the operating condition analysis mode to OCD, you are making sure that you are accounting for the on-chip variation for the physical effect. CRPR, you are making sure that unnecessary pessimism does not harm your parts. In the clock uncertainty, you have to adjust for, you don't have to now estimate the clock skew. Clock skew would be real, calculated, so you need to reduce this value. Now we will do update timing. Now update timing will give a lot of messages. Many would be for some drive resistance is being too low, and so prime time has adjusted the drive resistance to improve accuracy. Such type of messages are okay, they are not harmful. Next is very important when it gives this PT016 kind of messages. Now if you remember, we discussed about the if you have two clocks of different frequencies, how does prime time calculate the setup and hold effect? Now in the first rule was that it will expand the analysis time period to the LCM of the two clocks confirmed. So now the LCM for each we will do report clock. Now see, we have P clock, SDR clock, sys clock, and now we have sys clock 2x. So we told prime time to create sys clock. So the second part of the report is about generated clock. We told prime time to create a generated clock, and we gave this as a master source, and this is a generated source. So prime time has determined that this clock is reaching this, and the waveform is multiplied by 2. Now let's say if this pin had multiple clocks reaching it, which can be possible, which is possible, then you should also give master clock source as an extra argument to create the generated clock. Ideally, you only need to give name, master source, generated source, that's it. But if the master source has multiple clocks, then prime time will not know which clock to use as the master clock. So then you also need to specify. Otherwise it's fine. Otherwise it's okay to give only master source and generated source. So you can know more about it by looking at create generated clocks minus help. So you have a master pin which is compulsory to give source, and then master clock is essential if multiple clocks are present in the master pin. So it has other options also, edges, what we discussed, edges, multiply by, divide by. So you can read more about it. There are so many options of you can. In many cases we have complex generated clocks. So this generated clock command is very powerful. It will handle almost all the cases. Now, now we have 3 clocks. One period is 5, other is 12, other is 15. So it will expand each clock to the LCM of these 3 or these 4 other, and the LCM of all these is 60. So it will expand it to 60. Now assume if one clock had a period like 33 or 17, the LCM will be still greater. So you have to look for these messages in update timing, expanding clock. If the clock expansion period here is too large, then you have a problem, right? Now what I'll do, I'll simply do, now we loaded the parasitics, we saw how to make sure that parasitics are okay by doing report annotated parasitics and looking out for error messages. We saw how to create multiple clocks, how to create a generated clock. Now let's do a report timing. I'll just do a report time minus no space. So this will give me, just to repeat, this would give me the worst path for each path group. One worst path among all the path groups. So this is what it gave me. Let's output it into some report and then look at that report. Now this is a setup report. Obviously it's I did not give anything for the default setup report. Path group async default. Async default is for recovery removal. So it's showing me that now see, this is where the problem occurs. Now we see that since there is no we haven't defined any asynchronous relationship between the clocks, so all the clocks are considered to be synchronous. So now it will decide on edges. Now this is an assignment for you, that you know that sys clock period is 15, sys clock period is 15, SDR clock period is 12. Now you have to convince yourself why did the setup edges, why is the setup edge 45 and 41. Remember, you have to examine all the setup edges within the LCM period, which is 60. So one thing is clear, what an experienced person could tell you quickly is that, okay, period 12, period 15. That means, so see, you have to also see that what is the launch flow. Launch is sys, capture is SDR. Launch is sys, launch is 15, capture is SDR. So down the LCM, it will happen, down the period, it will happen that some SDR clock edge. So first, it will be the rise will be at, both rise are at 0. Now in this case, I haven't specified any waveform. So for both the rise is at 0. For this, the rise edge is at 0. The capture is at 7.5. For this, the rise is at 0. Capture is at 6. Right? Since the waveform is similar in the sense they have 0 rise, the period difference is 3. So at some point of time during the complete LCM period, it will happen that this clock, if this is the capture clock, will capture after a period difference of whatever is the period difference. So here you see the difference is 3, and here if we see sys clock 45, SDR clock 48, the difference is 3. So it will happen. For hold, if you do not give any specify any waveform, and since the edges are coming at 0 0, the checking will always be performed at 0 0 in most of the cases. So, but don't take my word for it. Draw the waveform on the paper yourself. Convince yourself that if the sys clock is launching and SDR clock is capturing, if prime time has done a correct job of doing 45 and 48. Second important thing, clock network delay propagated. Clock network delay propagated is the sum of, it is the total clock latency that prime time is calculated. So it is giving a propagated figure. It will give just a figure here if you don't give any option in report time. So 45 is the rise edge, plus 3.09 is the propagated, plus this you already know, clock to queue delay. I'll expand this report timing each and every time. So I'll tell you the major figures here. Clock network delay propagated. These are again gate delays. Then the capture edge. Again, it will give clock network delay propagated. Now see, this is the skew. 3.09 is the propagated delay for sys clock. 1.96 is the propagated delay for SDR clock. There is a skew difference. And this is where the clock relationships are very, very important. Now, clock tree network needs to know whether two clocks are synchronous. If the two clocks are synchronous to each other, it will build a common clock tree because it needs to balance the skew across. So, skew balancing is needed for all the parts which interact with each other. If the two clocks are synchronous, then there will be timing paths between them. And the clock tree synthesis algorithm will consider that and build a common clock tree. And so the skews will be within some particular strict limit. If in the back end the two clocks are deemed as asynchronous, then there will be independent clock trees and their skews will not match. So if in back end, if in clock tree synthesis, two clocks are deemed to be asynchronous, but in STA you are calling them synchronous, then it's a problem. The skews will not match, right? Now here we see that there is a clock network being propagated, and this is the proper skew 3.09 minus 1.96. Clock reconversion pessimism is 0. Why is 0? Because there is no common clock path. I'll explain this further, but here it's 0. CRPR is 0. This is also one indication now. One indication that these clocks are asynchronous. Now, see, as an ST engineer, obviously this will not be the case for people working in the industry. When I started on this lab, I did not know anything about the clock. I just decided some arbitrary clock period, and I did not know whether these clocks are asynchronous to each other. So I decided not to assume anything. I did not set any false count. But now I see that first indication, skew is mismatch. 3 and 1, 1.96. There's a big difference. 1 nanosecond is a big skew. One indication that they are not synchronous. Second indication, there is no common path. These both are coming from primary ports. So there is a second indication that they are asynchronous to each other. Let's see other reports. Then here it's a sys clock and sys clock. So here it's good. Sys clock to sys clock. So now we see good. This is an example of a half cycle path where the launch clock or latch is working on a negative edge. So now usually when a path is launched by sys clock, captured by sys clock, usually it will be full period long, 0 and 15. But here the launch point is the negative level sensitive latch. Now since it's negative, the launch active edge here is a fall edge. So this is the fall edge. This is the rise edge capture edge. So now you get a period of 7.5. See here the CRPR has some value. So it is delaying, CRPR removal is delaying the capture clock. When you delay the capture clock in case of setup, it is an advantage. So CRPR is a pessimist removal. It is not a pessimist addition. Pessimism, if you don't do CRPR analysis, that means extra unneeded pessimism is added to your flow. CRPR is a process which removes this pessimism, so it will credit to the slack, right? So this is one example. Let's go further. This is an input group. It is assuming some zero input delay because we haven't specified any input delay. Now here also, in case of multi-clock till clock, now you cannot give single input delay with respect to one single clock to all the inputs. You have to know design wise which inputs talk to which clocks. For example, here this report, without even giving any input delay, this report tells me that there is a path between SD, this pin, and this clock domain. So I know that yes, this pin SD DQ pin should be given some input delay with respect to SDR clock, not any other clock. Assuming if let's say SDR is asynchronous to all other clocks, then I should be very careful. Now let's say you are working at a chip. Some of the inputs go to memory controller, other inputs go to CPU. Now you should not assign input delay on memory controller ports with respect to the CPU clock. You should respect the domain. Assign input delay on the memory controller port with respect to the memory controller clock. This is what here we have to do. SD pins are, the name suggests, they are related to some SDR interface, memory interface. SDR clock is again a memory clock. So these pins should be assigned input delay with respect to SDR clock only, not with respect to any other clock. So things become a bit more complex, a bit more detailed when you go to when you have multiple clocks, right? So you have to be careful. Now, so we have applied clock uncertainty to all the clocks, which is getting subtracted here, and rest all you are already familiar. Let's move ahead. Again, we see the path from SDR clock to P clock. Now here the problem is that we are only getting, again, the skew mismatch here, 2.85, 1.97, one evidence. Second evidence, both of them are coming from the ports, so they have no common clock, logic, clock logic, so CRPR is 0. CRPR, I again repeat, clock reconvergence pessimism removal can only happen if you have a common clock path between launch and capture edges. So here also, since both the clocks are coming from primary ports, there is no common path, so CRPR is 0. The report timing report also tells us what are the derates. And now with the present clock frequency, we see that the launch edge is 24, capture is 25. Something wrong. There is 1 nanosecond difference. 130 nanometer logic cannot work at 1 gigahertz. So it appears that SDR and P clock are again asynchronous to each other. So again, you have some strange relationships, 22.5 and 24. So if you don't declare if you have such periods, and if your spec actually says that your clocks should be asynchronous to each other, and if you don't declare it as such, you will have a lot of strange timing reports to them, like this launch at 22.5, capture at 20. These are strange numbers, right? As my experience says. So what I'll do, I'll clean up this, but as an assignment, just do one exercise that assume the two clocks to be, one clock to be 15, other clock to be 12, and tell me what are the launch and capture edges. The answer is here. You have to just make sure that you understand it. So in this case, it's 45 and 48 in case of setup. Remember, here the launch is 6, capture is SDR. Launch is 15, capture is 12. Let's see. So let me go to the specific case now. From get clocks, sys clock minus 2 clocks SDR. This is how I do specific report timing, and again 45 and 48 is okay. I'll add minus no split to make it clear. Right. Now see, when I did this, there are two timing reports here. One is the async default. So async default, since it's a different group than the clock group, so it will give me again any report timing command. it will try to give me whatever path group is satisfied. For each path group, it will give me the worst clock. So in this case, the capture clock is SDR clock, but here also for the async default also the capture clock is SDR clock, but since it's a recovery removal type of check, it's grouped under async default, so it will give me the async default report, plus it will also give me the regular H2H report. So 45 to 42. Okay, now let's make things more interesting. I will now report the hold time. I'll say hold time. How do you report? You said delay type min. Now here it's 0 and 0, which is what I told you. Always, if the two clocks, you don't give any waveform numbers, if you assume the rise edge is 0, and if you don't have asynchronous relationship, if you don't define false path, then the hold edges in all probability would be 0 and 0. You can verify this by again drawing it in your on paper. Draw the waveforms. Make sure you understand how the edges are calculated. You can do the other way around also now. Let's say -2 and -. Delay min is okay. 30-30. 30-30 is same as 0-0. No difference. But here, so see here it's 0-0. Here is 30-30. So 0-0 is exactly same as 30-30. It's no difference from. So sometimes prime time will go to the. So it's saying 30-30 here. Why? Because there's a fall edge. So there's a fall edge here, and there's a rise edge, and why this is a fall edge? Because it has some falling edge trigger flip flop in somewhere which is launching the data. So it will give the fall edge, and it will because the fall edge is at 30, the capture is at rise is at 30 for hold. So 0-0 is same as 30-30. Prime time will shift the edges when it comes to negative edges, right, for hold. So understand this between both these clocks to and from. I'll again give the setup report. So now see it's 12 and 15. Now this is very clear. If you draw a figure, this will become very clear because now the launch is SDR, capture is this. The SDR rise it comes at 0, then again at 12. For sys clock, the rise comes at 0, the capture comes at 15. For the capture clock, the capture edge is coming at 15, the rise edge is coming at 0 and 15. So at the 15, the launch edge of the launch clock's launch edge just before this is 12. So it's 12 and 15. Similarly, you will see that how it's 45 and 48 when you when you do vice versa, when you launch from SIP and capture from SDR. So as an assignment, draw the waveform on a paper for both these clocks. Assume one clock to be launched, other clock to be captured. Do it for both the cases. Fix the clocks then, and make sure that you understand what are the launch edges, what are the capture edges for both setup and hold. Do this exercise and make sure that you understand it completely. If you don't understand it, go back to the lecture slides in which we discussed this concept. Read the man page, read the documentation, and make yourself very comfortable with this. Right. Now I do the actual stuff. Now I have seen that there are evidences that these clocks are asynchronous to each other. Now I will apply false paths. Now since I am not doing noise analysis, I can use false paths to declare my clock relationships. It is alright to do this if you are not doing noise analysis. Now, one thing you have to be careful is that in this design, sys clock and sys clock 2x are not asynchronous. Sys clock 2x is multiplied by 2 of sys clock. So you should not by mistake set a false path between these two. So how I do it? I do something like this. There are many ways to declare false paths between a group of clocks. Many people will write some typical procedures. Many people will do some more sophisticated, but we will do very basic stuff here. We will just we will not write any procedure. We will write the clock names itself. So here I say minus from get clock, list sys clock and sys clock 2x. I am grouping them in the same list because they should not be set false path with respect to each other. So now prime time will apply false paths from sys clock and sys clock 2x to P clock and SDR clock. Now secondly, I should do P clock to this group. So then I do from P clock. I do from P clock to sys clock 2x and SDR clock. I do like this. Then I do the last case, which is from SDR clock to sys clock 2x and P clock. These three statements make sure that sys clock and sys clock 2x are synchronous. From this group, between this group and P clock, they are asynchronous. Between this group and SDR clock, they are asynchronous. SDR is asynchronous to P. So these three commands will make sure that you have proper clock relationships defined. Any change in constraints, I have to do update timing. Even if I don't do it, the next command I run will force it. So I'll do update timing. Now see, prime time is giving me one information now. One information of about PT016. It's the code PT016. It is expanding sys clock 2x. Now let's report clocks. Let's do report clocks again. Sys clock 2x period is 7.5. Sys clock period is 15. Both of them are synchronous. That is why prime time needs to expand the period of sys clock 2x to 15. The LCM of these two, 15 and 7.5, is 15. It's a typical case of master clock and a multiply by 2 or a master clock and a divide by 2. It's a typical case, right? Now my constraints are good enough except input and output delay. Now let's look deeply into what all options does report timing have. Let's understand how CRPR works. Let's do some clock analysis. Let's do what an STA engineer will do during the process of making sure that his constraints are correct, everything is correct, right? And later we will come to the point. Now this is, so this analysis, this session, lab session will focus on how to debug stuff, how to understand timing reports and make sure that the constraints you have specified, the rates you have set, and everything is in place, it is correct. And the second part, the later extension of this is now you analyze violations and you try and fix them. As an STA engineer, the job is also to help fix the violations, right? So we'll look into that later, probably in this lab or as an extension of this lab. Now there's a very interesting command called report clock timing. Report clock timing helps us in analyzing a particular clock in terms of its latency and speed. Now it has a lot of options. It has almost a lot of options which are common to report timing. Why? Because they are from and to and setup and all and so on. So one example I'll show you. I'll say report clock timing. Is there a minus clock option? So yeah, it has a minus clock option. Otherwise, it will do for all the clocks. So let's do it for one clock first. Let's do it for PCLK, and the compulsory option is minus type. Now it's asking you what. So let's give minus type skew. Report clock timing minus clock PCLK type skew. Now it will tell us. Now okay. Now there will be a bunch of registers driven by this clock. So what we could do is we can say, how do I know this? I can do all registers minus clock P clock. Now this way, this is a command you can write to list down all the registers that are driven by P clock. So now among all these registers, so I'll give you one more interesting command. It's called size of collection. So now let's say I want to know the number. It's frozen. Looks like the session is frozen. Yeah. So before clock timing minus, so I was showing you an interesting command, which is so all registers minus clock clock PCLK will give you a list of all the registers of clock. You can any command that returns a collection in pickle, you can do a size of collection on it, and it will give you the number. So there are 1076 registers on register P clock. Now this command report clock timing minus clock name and type skew gives us among these 1076 and clocks, it will give us the clock that has the best latency and give us the clock that has the worst latency. So this block here has the best latency of worst latency of 2.86. This clock here, the clock pin of this clock has a best latency of 1.89. This is the CRPR among these two, because there will be a common clock period. Although there might not be a path between these two, there might and might not be a path between these two, but it will show you the latency, it will show you the CRPR and the skew. Skew is the difference, so the difference adjusted by the value of CRP. Here it will tell what is the edge, whether it's rise, so it's rise. P means clock is propagated, and minus plus are just like what is the rise edge, what is the launch, and what is the capture edge. Now, so with this command you can analyze the quality of the clock tree. You can also say minus type latency, and now it will give only, right now it's giving only one clock with a particular it will be this same clock. It is giving the latency to be total latency to be 2.89. Transition IPCI core mega. Yeah, okay. It is giving us some clock and it is giving latency value. Now you can give. Okay, so no. Okay, I'll explain it again because I had explained it wrongly in terms of skew. Let's analyze latency first. Forget about skew. I'll correct on the skew part. On the skew part, if you give minus inverse to be, let's say 50, and I'll give minus no split. So among all the 1076 clock points, it will list down the latency in the decreasing order. The clocks with the worst latency figure will come at the top, and it will keep on decreasing. So we see that these are the list of clocks that have 2.89 latency. Everything is 2.89. We can increase the significant digits to let's say 3, and we see that this is okay. It's same as, we can even do let's say 100, and so it tells us that okay, it shows us that in decreasing order of decreasing latency. So it also tells us what is the transition, the source latency, which is 0 for everything. We haven't specified any source latency. Then this is the I think this is the rise latency. This is the fall latency. Yeah, this is the rise edge, or this is the fall edge. This is the rise edge. So minus plus I guess means that fall and rise, and yeah. So this is the fall. This is the rise. Now skew is different. It's skew. That's what. Okay. Let's do skew again. Now among all the timing paths on this particular clock, it will give which timing path has the worst skew. That's why the CRPR appears here. It tells us that this path has the worst skew. Now these two endpoints might not have the worst latency or the best latency, but among all the timing paths, these two particular clocks have the worst skew. So there will be a timing path from either from this to this or from this to this, and this is the worst latency, the worst skew. The skew number is calculated as a difference of these two adjusted by the CRPR value. So this is the skew. So see the actual skew number. So skew matters only when there is a timing path. First important thing, the clock tree synthesis tool will try and match the clock latency figure for all the clocks on the clock tree. Let's say for this clock has 1076 clock, it will try to match these two numbers. It will try to match latency. In fact, it will try to keep a latency within a tight range for all these 1076. Skew is the difference between the clock latencies of any two clocks, but there should be a timing path between these two clocks. Not all clocks will have timing paths with all, right? There some clocks will not have timing paths to other clocks. So this skew number here, minus type skew, gives you the worst skew number, and actual clock skew is always CRPR adjusted. If you take the value without CRPR, the skew is 2.86 minus 1.89. Skew is about 1 nanosecond, but the skew has to be adjusted by the CRPR value, otherwise it's not a real skew because of the delays. Because in the common clock path, in the same path, it's treated, same cells are being taken as max delay in one case and min delay in another case. They have two separate delays, which is not possible physically. That is why actual skew number is 0.27, which is good. For this clock, the actual skew number is 0.27. You can change the clock here, you can do this clock, and the skew here is 1.34. This is bad. Now this might also happen because of if there is some generated clock logic. Now consider that a clock has a generated clock logic on it. So there will be the master clock and there is some generated clock on it, and there is another cloud of logic. Now for any generated clock logic, CTS will keep the generated clock logic out of the skew part. It will not balance. Why? Because the generated clock logic will not have regular timing paths. A clock divider, for example, will not have a regular data path, so it does not need to be. It does not need a. Usually, if there is a generated clock and if it's balanced, if a clock that is generating a clock, and if it's balanced with the rest of the group, it will have a very big latency. And always we want to keep the clock latency to lower. The lower the clock latency, the better is the timing because of the OCD effect. You have to understand this. Consider this. Give some thought on this. The larger the clock latency means the larger the delay from the clock definition point to the flops. The larger the clock latency, the larger portion of the clock tree will be non-common. Increasing the non-common clock tree part will affect your timing, negatively affect your timing. So all the tools will try to keep lower and lower latency. So a clock that is generating a clock from a master clock, it's a clock divider, need not be balanced with the rest of the logic. In such cases, you can see some skew numbers. So skew numbers are just a measure of the clock tree. They are not a measure of the timing. We will see timing afterwards. So this is the command report clock timing, which you can use to analyze the clock tree. This is not a very famous command. This is not a very highly used command, but you should understand that such a command exists, and you can quote some skew numbers and some latency numbers using this. We use this command for a very specific case. When you go to industry, you might find some application that requires the use of this command. Now there is one more command. We have already seen this command, check timing. Now let's run check timing here. So check timing is a very useful command. So if let's say you forgot to define some clock, check timing will tell. It will tell here that there are some clocks which have no clock. I'll show you a check timing report, a verbose report, which is without clocks. I haven't defined any clocks for a particular design. So this is the kind of report it gives. It tells me there are unconstrained endpoints. Unconstrained endpoints are because of the clock being absent. Plus it will give me a list of, this is a check time verbose report. It will also give me a list of registers with no clock. These registers don't get clock. Checking no clock. It gives the number and a list of registers that don't have clock. So it also tells unexpandable clocks. That means if you have clocks with weird periods and they are not, if the LCM is pretty big, or if the generated clock is not connected to the master clock in the netlist system, or there is some difference between the generated clock definition and the netlist structure, then it will give an expandable clock. That means that it is not able to, an expandable means it is not able to find out the period of the generated clock. So it will give warnings here. So this is a very, it will give combination loops warning here. It will give generated clock related other warnings here. So you need to make sure that check timing report is clean. You understand all the warnings here before proceeding to the timing reports. Now let's look at report timing. Now I will again do report timing and do minus no split. So again it will give me a lot of things. Now let's analyze only one particular timing report and look into detail what it all it has. Let's look at just clock. Now sysclock gives me this particular report. So we've already seen. So we now keep expanding the. Now here important point. The first part here is launched by sysclock 2x, not by sysclock. It is launched by sysclock 2x. It is captured by sysclock. Now please note that a particular clock can get multiple clocks due to some reason. There can be many reasons. Now let's first analyze. So how do you see that a clock gets multiple clocks? I'll tell you about. We can know this by doing a check timing. So check timing by default has an include list and a, so it has a multiple clock option also. So yeah, so by default it doesn't check. Let's try and include this. Include multiple clocks. So it will check. So it's telling me that timing is enabled multiple clocks per register is set to true. So if you set this variable to false, then prime time will give warnings when registers have multiple clocks. But right now it's set to true. Actually, it is possible in static timing analysis. It is very possible. It is used also that multiple clocks can reach particular register. Now let's say there are two different clock sources which can reach a particular logic, and they are depending on some mux selection. Now, as an amateur, you might choose to set some case analysis on this mux and propagate only one clock at a time. But as you become more experienced, you realize that you don't set any case analysis on this particular selection. You let both the clocks through, and so you can analyze both the clocks at the same time. There's no harm in doing that. It's actually SP allows you to do that. So that is why this variable is set to true. So we will see this. We will debug this later. Let's look at the report timing again. So now see this that sysclock 2x rise edge is 7.5. Call is at, capture is at sysclock. Capture is sysclock. It has 15. This is expected because sysclock is twice. It's multiple. Sysclock 2x is multiplied by 2 of sysclock. So the edges are, the period is expanded to 15 because the LCM is 15. For cases, you can again verify this on paper. For cases where you have launch from a clock and capture by a 2x clock or the other way around, the period you get is equivalent to full cycle of the faster clock or half cycle of the slower clock. Both are same. In this case, the faster clock period is 7.5. The slower clock period is 15. So if you launch from one and capture at another, the total period you get will always be equal to one period of the faster clock, that is 7.5. You can verify this. You can verify this by making the waveform. So here the launch is at 7.5, capture is at 15, which is expected. So anytime you have a launch and a capture between two clocks that are either divided by 2 or multiplied by 2, the period you get is one period of the faster clock. Here the faster clock is sysclock 2x. The period is 7.5. What is the difference here? 7.5 and 15. The difference is again 7.5. So this is a setup check. You can even do this the other way around. Sys clock. Let's see what is the worst part here. Sysclock 2x. The worst part is from sysclock to sysclock 2x. So again 0 and 7.5. So again, whether the launch is slower or launch is from faster, the period you get is one clock period of the fast clock. So here it's 0 and 7.5. Okay. Now let's explore a couple of options in report timing. So I'll keep this report timing as it is. I'll expand it further. Now there's a type. There's a path type which is very useful. Now this path type is default. This path type is normal. You can have a summary. You can have a summary path like this, or and you can add things to it. You can add input. You can add net. You can add transition. You can add capacitance. I'll add these and see. This is what now the timing report looks like. Let's. I've already explained this in one of the labs, but let me explain something. Fan out. When you give nets, it will start giving fan out information also. So we'll know how and when it fan outs. again it will report transition and capacitance. If you are doing pre-layout, you will not notice this ampersand sign. This ampersand sign is only for post-layout. It tells you that RNC is annotated for this, and prime timing is doing delay calculation based on that. So if you don't see ampersand at some point, it means that prime time is either doing dial load or not doing anything. So you have to investigate that. So you have to see. So if you have made sure that you have no errors while reading parasitics, if you have made sure that your report annotated parasitics, you don't need to look for ampersand. But I'm just telling you for information that ampersand means that this is an annotated delay or calculated delay from step. Okay. Then now it will also show inputs of every cell because we have enabled minus input pins. Now clock network delay propagator. This is very important here. But still we see that path is starting from the clock pin of the launch clock. Here the launch clock is rising as triggered. This is the launch clock, operand B reg, and path is starting from this. What about the launch clock clock? Launch clock path is compressed here. It is represented by a single statement. Clock network delay propagated. Let me open a PPT here just to. Yeah. So we see that actually the path should start from this. The path should start from somewhere from here. Clock launch path. It should show us the launch path, then data path, and then the clock capture path. But here it's not showing me the clock launch path. Clock launch path is represented by just a single command, single statement, clock network delay propagated. In case of pre-layout, this comes as ideal because we set the clock to propagated mode. It is now propagated. It is showing me a complete, just a symbol delay value. I will expand this further. Second thing, again, capture clock network delay is also propagated, compressed. There is no information. Clock uncertainty, CRPR is fine. Now let's expand. So now there's an option called, we will remove capacitance and transition for a while. We will add minus path type, full clock. This will show me the full clock path. Now see the report has length has increased. Now see it will start from the port. This is very important. Now it starts from the port. It is now showing me the launch path as well, launch clock path. Clock goes to pad, shows me the incremental delay, shows me the cumulative delay. It goes to some clock mux logic. There's a clock multiplier here. There's a clock multiplier 1x. This is a, so every time it is showing the reference also. This cell is of type this buff D2. This cell is of type buff D2. This is a net. This cell is of type mux, and so on. And it goes to something. It goes to OSIS 2x clock, and then. So now and then it reaches then it reaches, goes through some logic and reaches this. So here 3.04, it reaches at 3.04. Now the timing report starts from 0. In the earlier case, the timing report started from right from 3.04 because the latency was 3.04. So by doing minus full clock, you can do some, you can expand the clock logic. You can see the actual launch path. Let me output it to report and we'll see this. So this is how you see the complete clock path. It also tells us what are the options that you give. So this is how you see the complete clock path. And second, at the capture part, now also you see that now here this strange thing. Still the clock source latency is coming out to be 0.98. In the launch part, the clock source latency is coming out to be 0, which is expected because it starts from the clock generation point. But at the capture part, since it's a generated clock, this clock means not a primary clock, it's a generated clock. So still it did not give us the complete path for the generated clock. This is the generated clock latency. This is known as the generated clock latency. But it starts at the generated clock creation point, which is this. If this latency, generated clock latency is 0, then there is something wrong. If you have defined a generated clock and there is a clock generation logic, it should be timed. It should be correctly timed. Then only it's correct. If the figure here is 0, there is something wrong, and obviously you will get some check timing messages. You will also get messages during update time. But we did not get any messages, and we have some figure here, right? So it's correct. And then we also see the clock capture path as well. It also that's it. You know everything. Clock reaches the clock pin here. There is a CRPR credit given to you, clock uncertainty, and so on. Right. So this is now how do I see the generated clock network as well? There's an option called full clock expanded. So the types were summary, full clock, and full clock expanded. The default thing where we see just the one figure, the propagated figure, is the full. So they are summary, full means full data path, full clock means full clock path, full clock path expanded means full clock along with generated clock report also. Now let's look at the timing report. The only thing that will change is for the generated clock. Now for the capture, it's again starts at 0. Now it starts at 0, it starts at the master clock again, which is same. Sys clock is same here. It goes to pad and then it tells us this is the G clock source. This is the generated clock source. This is how you see and make sure and verify that the generated clock latency is being calculated. You do report timing, and this is where report timing is so powerful. It has so many options. It gives you so many options to report. So this is where we are getting we got generated this is how prime time calculated generated clock latency, right? So what is the generated clock latency from here? This time minus this time, 8.48 minus 7.5, which is 0.98, which is what we saw earlier. So now since it shows the complete clock propagation, it doesn't show a combined latency figure. Right? It is not showing a summary latency figure here because we have used the expanded option. Now, does it show common? Okay. Now let's talk about CRPR. Now let me report a simpler report. I'll say minus group sys clock and from get clocks sys clock. Now this is where I am saying that report timing, give me a report, the launch sys clock and the capture is also sys clock. So capture is controlled by the group option, launch can be from to sys clock, get clock sys clock. Now here I haven't done minus expanded, that's alright. Now I see, okay, I see some figures here. I see that launch is at 0, capture is at 15, which is okay, and I see all the delays, fine. Now let's talk about CRPR. For hold, for setup, this is a setup report. Setup, it will give you the credit and move the capture edge to later point in time. Capture edge after network delay is 17.63, it will add CRPR. It is giving you credit. Anything that moves your capture edge later in time for setup check is helping you. I'll do this for hold. CRPR value, it will move the capture edge back in time. Anything for hold, if it moves your clock capture edge back in time, is helping you, is giving you credit. If the CRPR was not there, this slack would have been worse by 0.19, minus 0.87, minus 0.19. This would have been the slack, if not CRPR, if not because of CRPR. CRPR is reducing the slack by 0.19, right? So this is how you understand CRPR figures. Let's go back to setup report. Now let me give you something else. Report delay calculation. This is a report CRPR command. I can say report CRPR from. Now CRPR is between clocks, so you can do this and to this. Any two launch and capture, you can do a report CRPR, and it will now tell you something. It will tell you first what is the common point, and does it also report the common point using something? So let me also do a report timing and minus path type full clock, and yeah, and I'll do a report CRPR. So this is the common point. This is the clock common point, which is iBlender and buff BD G6 B2 I8. So we see that this is the common point. So in fact, the common point is right before the capture edge, and for the launch, this common point is the common point, and it diverges from here. So it is telling me that this is the common point, which is from this figure. This is the common point we are talking about. The after 1.2 ns on the clock network, this is the common clock path. It also tells me what is the launch edge at common point, what is the capture edge, rising, arrival time, early, late. Now this early and late arrival timing are only because of, mostly because of, it can be because of different paths also, but here let's see the path. Here the path is going through a MUX, yeah. So it can be because of different paths, or it can be because it's not because of different paths, because the common clock is the common path is common, it's unique. So it is because of the CRPR, it is because of the delayed values. We have given delayed as 1.1 and 0.9. So it is telling me that let's only worry about the rise edge, because the launch and capture are both rising. It is doing it for both fall, rise and fall. So early is 2.29, late is 3.31. The actual delay is between these two values. So the actual delay is most probably early is 2.29. So what I'll do, I'll divide 2.29 by 0.9. So actual delay is 2.54 and about 2.54, and 2.54 into 0.9 is the early delay, which is 2.29, and actual delay into 1.1 is the it is strange 3.31. I have to see what it is. I have to double check. So early is 2.29 because it is deleted. Let me take the delete value. It's 1.1 and 0.9. Okay. So it's 2.29 is the early. The late is 3.31, and the CRPR, the difference is 1.02, which is giving the edges match time, which has rise and rise edge, and CRPR value of 1.02 is given back to you. So this is how you debug CRPR numbers if you have to. Otherwise, if everything is going fine, then so just make sure that whenever you are worried about clock skew, you have to take into account CRPR value, because clock skew, actual clock skew, the real clock skew is the reported clock skew adjusted by the CRPR value. Right. So, for example, in this report, particular report, you say that okay, clock network delay propagated is 2.63. This is 3.7. So the skew is more than 100, but the actual skew is that number adjusted by 1.02. So the actual skew is pretty good in this case. So this is how you debug CRPR. Now let's talk about the rate. I was talking about the rate. Let's come back to the rate. Report timing is an option where you can give minus the rate, and it will also start reporting the rate. So let me, yeah. So now it's telling me that we will, let's give minus path type full clock. And redirect it. So here we are given minus rate. Now it's also started showing me the direct numbers. Now I have given the late delay to be 1.1, so it will multiply all such timing. So this is already multiplied timing. It is showing me the delay. It multiplied all such. This is after multiplication. These delays are after multiplication. It multiplied the launch clock edge, plus it multiplied all the data path by 1.1. So everything in the launch part, in the first part of the report, will be multiplied by 1.1. It's already multiplied. It's just showing you the multiplication factor. Everything in the capture is already multiplied by 0.9 because it is the early part. So remember, for setup, the launch clock path and the data path are taken as maximum. The capture clock path is taken as minimum. It's early. So this is early, right? And at the end, it also gives me a derate report summary. Total derate required time is 0.29. Arrival time is minus 1.21. Total derate slack is 1.51. That it's telling us that the total derate applied in the required time is 0.29 by multiplying it by 0.9. So all the figures, the derate effect is 0.29 for the required edge, for the capture edge. The derate effect is 1.21 for the launch part. This derate effect is more because the data path is bigger. Plus it also has a launch clock path. The required time only has the clock capture path. That's why the derate effect is less. Slack is 1.51. Slack with derating applied is 5. CRPR due to derating is minus 0.56. Slack with no derating, that means if there was no derating, what would have been the slack? The slack is without derating is 5.95. That means, how did it come up with this number? 5.95. So this is the total derate, this is the total slack derate. If the derate was not there, then CRPR would have been not there, and the CRPR credit should be again adjusted. So 1.51 is the total derate that is applied. So this is minus shows it's late derate in the arrival time. So total derate is 1.51 plus slack with derating applied is 5 minus 5. So it will be something like this. 5 minus 0.56 plus 1.51. So this is the slack without the derate. How do I achieve? I'll repeat again. With the derate, the slack is 5. Now, what are the derates applied? Derate is 0.29 for required, 1.21 for arrival. Sum is 1.51. We add 1.51. This is the 1.51 is the time that derate has consumed. 5 is the slack with derates. So 1.5 is the time consumed by derate. We add it, so slack would increase. But now the CRPR credit is given back to us because of the derate. If we don't apply a derate, the CRPR credit will be taken back. So I will subtract whatever CRPR it gives me. This is the way it arrives with a number. So this is how you can also see the effect of the derate in report timing. Please remember, without derates, the OCV doesn't make sense, right? There has to be some derate to model the on-chip variation. So this is how we do it, right? And applying derates, setting the analysis condition as on-chip variation and CRPR, they all come under a single methodology of on-chip variation. So this is how you see the generated clock. This is how you see the generated clock expanded report. You see the derates. You see the OCV. You see the you can do a report clock, report CRPR. You can do a minus derate option and see all the derate values there, and so on. Right. So this is all the calculation about the report time. So we have seen. Now let's look at report delay calculation. Let's look at this report again. And now let's look at, okay, first look at the delay min report. Okay, I've already given delay min. Full clock. Okay, now we are looking at min. Edges are 0 and 0. Now it changes. For hold, For hold, the launch clock path and the data path are made to come early, so they are multiplied by 0.9. For capture part is delayed, so it's 1.1. Here it is showing me how much slack was, so this is violating by 0.87. It is showing me what is the effect of delay here, and it is adjusting using the same formula that we use for setup. It is showing us slack with no derating. So we see that derating in both the cases of setup and hold, it will make the path worse, right? Now you can do something like let's look at the timing report, a simple timing report, and let's do, you can at any point of at any time, if you want to see how did the prime time calculate delays, you can do something like this: report delay calculation minus from any pin to any pin. Now let's say I am doing from the input of a particular cell to the output of the same cell, right? This is where I am asking prime time to tell me the delay calculation for the cell delay. So if I do this, then it is telling me that let's again redirect it. So this is I am now focusing on a particular cell from pin. So it is telling me the units, it is telling me which library it comes from, it is telling me which cell we are talking about. We are talking about an adder cell between the carry in and carry out. It is telling me it's a positive unit, so it's telling me for the positive unit first. It is telling me the RC network, so it is telling me the number of elements on CO, R3 caps and 2 resistances. So it will add the total cap. This total capacitance is the pin cap plus the whatever cap it sees from the RC network, total resistance. Then here it is telling me what is the input transition time, what is the effective cap, what is the drive resistance, what is the output transition time, and the cell delay. This is where it calculates. So it will not show you the actual algorithm and formula it uses, obviously it's proprietary, but it will show you what is the input transition value, what is the output value for this particular cell. It will now show you for the so for all the, it will show you from input to output, it will show you for all the timing types that are defined in the library. So for here, for example, the first part is it is telling that RC delay calculation is skipped because RC delay calculation was not used for drive AR. Fine. We are more focused on the cell delay here. So first one is from to this arc strength is positive unit. Now it is telling us that here there is a condition positive unit, but the condition is A1 and B0. So it will give us for all the conditions. This is the condition A0 and B1. So for whatever data is defined in the library .lib, using that data, so there can be a conditional data also, timing type depending on the when condition, on some input conditions you can define the delay. For all such conditions it will output the delay calculation. Now I can also do delay calculation for a particular minute. Let's try that. Let's again look at the timing report and let's do now delay calculation minus from the output of a particular cell to the input of another cell. Now here I'm not sure what this message is, but because the RC delay calculation is not used, this is I'm not sure what this message is, but looks like there is some delay calculation because there are some caps and the resistances, so it will tell what is the net delay, what is the transition time, from pin transition time to pin transition time, and so on. Because this is now not we are not asking about the arc type is net, it is not cell, right? So it is telling me what is the RC network. It is telling me this message might be related to the CCS model. I guess we are using the MLDM model, so that's all right. So it is so for any section of the circuit of the design, you can do a delay calculation by using the report delay calculation. Now let's look at one more option in report timing called report timing. Let's look at all the, so report timing has the, I guess, the most number of options. So there is something called PDA mode. This is what we discussed. We discussed the graph based analysis where the skew calculation time will maintain one skew number skew number which is for the worst slew for cells which have multiple inputs. Prime time cannot keep the complete data. So what we could do, let's look at the worst violation first. Let's look at the report constraints minus all violators. What all violations? Let's now analyze this design for violations. So till this point, we have understood about the report timing, about all the options, all the famous options that report timing supports. We've already seen in the earlier lab about the inverse, about the max path, about how to give the path groups. Today we studied about the full clock expanded, minus derate, CR, PR, so on. We also learned about the delay calculation. Now let's focus on looking at the timing violations, right? What all timing violations are there? How many types of timing violations are there? Now let's do a report delay calculate. Let's do a report constraints minus all violators. So there are so many violations here. Let's do a no split. No split we do when you are writing to a report. Let's do all. Now this is what. So once you verified that you have applied all the constraints, you have set the operating condition analysis mode perfectly, your parasitic reading is correct, your clocks are correct, your clock relationships are correct. Then you come to you write some kind of report which tells you summary of all the violations. This is that report, all violations.rpt. Now it's telling me that PCLK has only one endpoint that is violating. For hold, it is first okay. Okay, it's telling me max delay there is only one violation. Now, so because it gives all the max delays at the first, then it is telling me min delay hold clock gating there is one violation, big violation. This is a big violation, might be false. Min delay input group, there are so many violations. We haven't really specified any input delays, so let's not give much importance to this. Again, so now PCLK has these many violations in hold. Again, SDR clock has these many violations for hold. This clock has these many violations for hold. A lot of violations for this clock, and so on. So it will give us again this clock 2x has so many hold violations. Removal, there are so many violations. Removal is of a hold type. Recovery is of a pickup type. So report constraints minus all violators gives us a good summary of how many timing violations are in the design. And now we've already mentioned that we are doing corner. It also gives us the max trans violation. So this is a max trans violation. Now we've seen that we talked about the corner based SPA, and we discussed that there will be multiple corners on which you do SPA. So ideally, on every corner that you do SPA, you would have to make sure that there is no setup and there is no hold violation. Or sign off, there is no DRC violation there. Now we see that there are some hold violations in the worst corner. So that means these hold violations are going to get bad. They are going to get worse when you move to the best corner. So this constraint file. So probably you would want to separate out this constraint file into two files. One file which will define the environment conditions like this, and second file which actually defines the clock. The second file will be common for the constraint file without the environment conditions, will be common for all the corners, worst case, best case corners, because they don't change. The clock definition will not change. But the first file which defines the link library will be different for different conditions. So you when you do the best case analysis, here you read the min dB and then you do the analysis. So I see that here there are a lot of hold violations, and these hold violations will get worse when you probably move to the best case form. Now let's look at one path. For example, here report timing. We saw that there is one set of violation in the timing. So we see there is one violation in the peak clock group, one set of violation in the worst case corner. So if I make sure that this violation is not there, then I'll only have the hold violations to take care, and then I'll probably go to the best case corner and do the analysis there. Now since I have only one violation left, I am very tempted to try out PBA. How do I try out PBA? I say minus PBA I don't do it for the complete group, right? So what I'll do, I'll narrow my choice. First, I have to narrow my choice. I say group PCLK and minus slack, so lesser than 0. Let's say for any clock, even you have, let's say, more than one molecule. This is generic approach which I'm talking about. So report timing minus group a particular clock, slack lesser than 0 will give me, and I increase the number of paths to, let's say, 5. Now in this case there is only one path, but again this approach is generic what I am talking about. Now for such case where you have, let's say, you selected a few number of paths with slacks lesser than 0, now you can give PBA mode and give exhaustive. So the option can be exhaustive, so you give exhaustive. Now see the slack is decreased a bit, although it hasn't given us a clean report, but it is saying recalculated 5 paths. Why? Because we gave max 5, returned 1 path. It first initially it had 5 paths, returned 1 path because only 1 path was satisfying this criteria. The maximum number of paths recalculated is 5. I don't know because it sometimes maybe the internal algorithm takes a look at the max path 5 first. It recalculated the transition number, and this will give, or this gave a better slack. So it gave us some advantage, but not a great advantage. But still, it gave us some advantage. In some of the paths which are very long, it will give a lot of advantage. If you have a very long data path, it will, the longer data path you have, the more PBA will give you advantage. That is why. So see, what are setup critical paths? Setup critical paths are usually the paths which have greater logic depth, which have more number of stages. Such paths, PBA will give more advantage because such paths will have cells with multiple things, and obviously some transition approximation because of graph-based analysis. Again, the thing to note here is that PBA reports the slacks will always be either better than or equal to the graph-based analysis. That is why we say that graph-based analysis is pessimistic. It is more conservative because PBA is an accuracy improvement over graph-based analysis. Second, when a hold paths are critical when the logic depth is less, when there is less delay. So PBA will probably not give you a lot of advantages for those. Why? Because the logic depth still is small. There are just 3 or 4, maybe 2 or 3 stages in the data path. So not a lot of PBA advantage. So this is how you do a PBA analysis. So in next lab session, I will talk about how to fix setup and hold times, what all to check before fixing setup and hold times. We will talk about a class of commands which come under what if analysis and time time. It's a slightly advanced lab, but it will be very useful when you go into the industry and work. So this is so till this point we have learned about how to set up the prime time session. We learned about parasitics. We learned about the constraints. We learned about different reporting commands. In the next one, we will explore how to actually fix timing analysis. We'll talk about that. Thank you.